welcome to everybody who decided to join our seminar. Well, we will have in coming month and also in January, we'll have 3 seminars devoted to Nobel Prizes. It will be the first one will be today on physics, the next will be on chemistry and medicine, and in January we will have a talk on Nobel Prize in economy, which is not really a Nobel Prize, but it is about not so much about economy. It is about let's say behavior of people in crowds. So it will be also very interesting talk. So I'm very happy that we at Sano were able to convince to give this seminar on Nobel Prize in Physics 2025 to convince Professor Adam Rycerz, who is really expert in this area, who is leading Department of Condensed Matter, Matter Theory and Nanophysics at the Institute of Theoretical Physics of Jagiellonian University. He was working in trying to research all these phenomena which have some origins in quantum and some, let's demonstrations in macroscopic level, because his PhD thesis was focused on strongly correlated atomic change, and then a series of research as a postdoc at different places in Europe was devoted to this, let's say, correlated phenomena. And well, I think that you can easily look at his bio on the website of our seminars, and as well as on the website of Jagiellonian University. And well, if there will be a need to answer a question during the talk, please ask the questions on Q&A or on chat. And of course, as usual, there will be a discussion after seminar. So Adam, screen is yours.
All right, thank you very much. I hope you already can see my slides. If something is wrong, so just tell me. First of all, I would like to thank for the nice invitation and nice presentation also just a few minutes ago. Okay, so today's talk is on Nobel Prize in Physics to Martinis, Clarke, Devoret and Martinis for the discovery of, let's say, macroscopic quantum tunneling in electric circuits, in short. So here are the Nobel Prize winners, as sketched on the web page of the Nobel Committee, and here are the photo of them, so you can see the difference between theory and the reality on this example. I will say a few words on their biographies, starting from John Clarke, because John Clarke was senior in this team. Actually, Martinis was, I think, on his second year of graduate study when this Nobel Prize discoveries were made. Devoret was postdoc and John Clarke was senior scientist. So John Clarke actually did a lot of research before. He was active, let's say, 15 years before this Nobel Prize research were done. So there is also a picture of the Davis, that is Davis for a Nobel Prize, just to focus a look on this. So as you can see, there is a bar of metal. This is actually niobium at the base. niobium is a superconductor in liquid helium temperature. This bar of niobium is partly oxidized, so let's say there is some corrosion on it, right? There is approximately 1 nanometer thin layer of oxide, right? Niobium is, of course, this bar is much thicker, but there is a thin layer of oxide to wear the electric contact, and then there is a top electrode made of lead indium alloy. So there are two different superconductors. Yes, and here is the sketch of the Davis. This sketch will appear several times during my talk, so maybe it's good time to explain the essence. So essentially, in a superconductor, a very tiny fraction of electrons is in the superconducting state. It's usually not even promille. So most of electrons act as a spectators, right? So superconducting electrons creating Cooper paths are governing electric transport, whereas the vast majority of electrons are spectators, right? So that's like in communities, or okay, doesn't matter. So because of this spectating electrons, this Josephson junction is also a capacitor, right? It also, we have two conductors separate the thin layer of insulator, so it's also a capacitor, and of course it's also an electric resistor, right? So we are drawing these three Davis's Josephson junction, capacitor, and resistor in parallel, but they are essentially all in one, right? That's it. And in this Davis used for setup, let's say, used for Nobel Prize experiment, of course, important part is also current source, right? So there is a Davis which, whatever is attached to this Davis, it drives a constant current, right? To constant and tunable currents to the system. And there is also let's say, source of microwave frequency perturbation, right? So alternating. Let's say there is a constant bias current, and there is also alternating current, probably screened such that there is no unwanted, right, perturbation, and there is also a voltmeter, right, measuring the voltage. If everything is in superconducting state, there is no voltage, right? So current is flowing without resistance, so zero voltage is measured. When something goes wrong, Josephson junctions stopped to be, so critical current is exceeded when voltage appears, right? So this is how it works. Okay, and prior to here, you can see Clarke on the conference in 2014. So I think he's still scientifically active up to some level. So he was talking about his pioneering research on, okay, this is actually a slide on the discovery of flux quantization, but he's also talking on Josephson junction and the famous experiment by Anderson and Rowell proving that Josephson junctions works as it was predicted. Right, and actually first topic in which Clarke was what Clarke is famous of is essentially his research on quantum interference devices called squids. If you connect two Josephson junctions in parallel and form superconducting ring, drive a current to it, then you can measure this critical current, right? So current at which voltage appears, right? And this current as a function of magnetic field and magnetic flux is periodic. With some appropriate tuning of the Davis, you can increase the accuracy. So this is actually the world's most precise magnetometer nowadays, and Clarke was a, I would say, equipment-oriented scientist building such Davises in 70s. In 1975, he also wrote a quite visionary paper entitled Application of Josephson Junctions to Computer Storage and Logging Elements, right, and so on. So it's not precisely on quantum computing, but at least the idea of using the Josephson junctions for computing could be attributed to Clarke. He was also studying something what is called pink noise, right? So it's quite a mysterious noise showing the frequency distributions creating like 1 over the frequency in different phenomena, right? It's they have actual Nature paper with Voss on this noise in music, speech, and other things, right? So it's quite interdisciplinary research. All right, so now let me maybe focus for a while on the point how many Nobel Prize were already awarded for superconductivity prior to this year's Nobel Prize. There are quite a few of them. First, of course, is 1913 prize for Heike Kamerli. Also, nowadays, it is usually referred as a Nobel for discovering the superconductivity. Right? Actually, the official citations for Nobel Committee was quite more a bit more general, but this is essentially for discovery or superconductivity. Then in 1972, there was a prize for Bardeen, Cooper, and Schrieffer for a very theory of superconductivity, now simply called BCS theory from their names. Then in 1973, there was a kind of combo Nobel Prize for tunneling effect both in semiconductor and superconductors, but half of this prize are actually awarded to Brian Josephson for his predictions, right? For his predictions of what we call now Josephson effect or Josephson effects. And he was 33 years old in the moment when he was awarded the prize. I think the record in this category belongs to Heisenberg, but actually is probably Josephson is surely one of the youngest Nobel Prize winners. Then there was a prize for Bednosh and Miller in 1987 for the discovery of high temperature superconductors. Then for Abrikosov, Ginsburg, and Leggett from actually the Leggett is the father of this concept of macroscopic quantum effects in a way that we understand them today. So it was also Ginsburg was also have created together with Landau the phenomenological theory of superconductors a bit preceding the BCS theory. Right, then I think Nobel Prize for Toulas, Hardon, and Kosterlitz could not be called the Nobel Prize strictly related to the superconductivity, but in some sense, in high temperature superconductor, you can also observe what is called Kosterlitz-Toulas transition, but it was this one I would not count. So we have 5, and then there is a 6th Nobel Prize, let's say, related to the topic of superconductivity. So as you see, there are quite a few Nobel Prize like this. So just to explain what is a superconductor, right? So superconductor is a system which has 2 features: zero resistance and Meissner effect. Meissner effect is simply repelling the magnetic field, right? So here is the enhanced plot by Heike Kamerlich-Ons from 1911, showing the resistance of mercurium as a function of temperature. So as you see, there is a sudden drop above 4.2 kelvins, but of course, from such a measurement, you never know whether this resistance is precisely 0 or is just very, very low, right? So there is another feature that is levitating. This is actually the magnet levitating over superconductor, but you can also do it the other way around. Okay, and here is there are, of course, plenty of superconductors. Most interesting properties belongs to alloy and compounds, very, very complicated systems. But here is just a list of elements, right, which are superconductors. Yellow are superconducting under atmospheric pressure, and the green one are superconducting under high pressure. For example, oxygen is interesting because oxygen, very common element. It became superconductor under 100 gigapascal, which is approximately 1 million of atmosphere, in below 0.6 kelvins. Right. So there are, in fact, if conditions are sufficiently extreme, most of the elements became convinced the superconductor to become superconductors. Interesting thing is, for example, titanium is interesting, right? Because in titanium, transition temperature depends strongly on the structure, right? It could be 0.3 kelvins, it could be even over 3 kelvins, but these are essentially elements are always, I would say, standard type first superconductors. Okay, here is the explanation. What is the difference between nice feature from old handbook? What is the difference between a hypothetical ideal conductor and the superconductor? So in principle, if you have hypothetical ideal conductor and you put it in magnetic field, you see that from Maxwell equation, you can derive that time derivative of the magnetic field inside ideal conductor must be zero, right? So you cool it down, and when you remove magnetic field, you would create a permanent magnet, right? As long as the temperature is low enough. So that would be hypothetical ideal conductor. In superconductor, it's not like this, because in superconductor, it's not only time derivative of the magnetic field vanishing inside, but also magnetic field itself, right? So if you put this superconducting material in the normal states in the magnetic field, then you cool it down and repel the magnetic field. And if you remove the magnetic field, there will just system without magnetic field, right? So it's how it looks like. And actually, type 2 superconductor, also called high temperature superconductors, from this point of view, are something between superconductor and ideal conductor, because they allow tiny vortices, tiny wires, let's say, filled with magnetic field, to penetrate them. These wires can also be anchored, right? So they cannot move. And if you plot magnetization as a function of magnetic field, so for type 1, so let's say element like aluminum under transition temperature is just ideal diamagnet, right? So magnetic response is equal to the applied field with the opposite sign. Right? Whereas high temperature or type 2 superconductor behaves similarly as type 1 superconductor up to what we call lower critical field. Then these vortices started to penetrate the magnet, and then this response is weaker. So why I'm talking about this is that there are very nice, actually, movies on the YouTube you can see. And if you have, regardless, type 1 or type 2 superconductor, in principle, it would be very difficult to do it with type 1 superconductor, but in principle, both type of superconductors can levitate over the magnet. But only type 1 high temperature superconductors with these anchored vortices can also be hung under the magnet like this, right? So this demonstrator is keeping strong magnet, and superconductor is just hanging below them, right? So the difference between type 1 and type 2 superconductors is that only type 2 superconductors can hang both under or over the magnet, right? That's it. Okay, so now let's come back to of course, these experiments by Nobel Prize winners were done with type 1 superconductors, for which BCS theory applied more or less. So the essence of BCS, Bardeen-Cooper-Schrieffer theory of superconductivity is on this slide. So eventually, in fact, they found that due to coupling interaction between electron and lattice vibrations, there is some tiny fraction of electrons near the Fermi surface which feel attractive interaction instead, apart from normal repulsive interaction, repulsive Coulomb interaction. But this attractive interaction appears only if electrons have exactly opposite momenta, opposite speed, and are opposite spins, and they are on the let's say opposite sides on the Fermi surface. And this pairing, this attracting interaction has several features that can be verified experimentally. First of all, if you take a look at spectrum, at the energy levels of normal metal, so there are essentially states occupied up to the Fermi energy, there are empty states, and there are what is metal? Metal doesn't have energy gap. Well, but a superconductor has some gap. The width of this gap is essentially 2 delta, where delta is for some reason called superconducting gap. So one of the interesting prediction is that superconducting gap with temperature going to 0 is related to the transition temperature by some formula that can be verified experimentally. These results, in fact, correspond to what we call BCS model, right? So you suppose this simple model of interaction as, of course, perfect isotropic, perfect symmetry of the Fermi surfaces.
Excuse me, this coefficient 1764 is just phenomenological?
No, this is an integral. This is an integral you can calculate numerically, right? This something with gamma function. Yes. That's I should copy such nice formulas, but yeah, this is something you can calculate. But you need to suppose a perfect spherical symmetry and the simple model of interaction, right? If you take a real dispersion relation of aluminium or whatever, then instead of a Fermi sphere, you have some very complex surface. So the coefficient would be different, but this is something everything is. So this is what we call.
Comes from the theory.
This comes from the model, right? BCS model, right? If you work with BCS model, you got some relatively easy integral. For more realistic models, the number would be different. So there are several experimental tests with which you can examine whether this BCS theory works. But this is probably most important because quite a few superconductors have, let's say, this number. Let's say agreeing with the theory up to 10%, more or less. Like if you take aluminium, nobium, or strontium, this kind of systems, they are not far from this number. Okay, so there is BCS theory. Then we have another phenomena which is called flux quantization. Actually, flux quantization is a first phenomena that could be called macroscopic quantum effect in the complex of superconductivity. I would maybe spend 1 minute on this. So the concept of Ginzburg and Landau, very non-obvious, which is what is called macroscopic wave function, right? So instead of considering a standard wave function like in quantum mechanics, which normalize to 1, right? Let's consider the wave function which have a square root of density as a numerical prefactor, and then phase in the exponent. So this wave function is normalized to the number of particles, right? So there are a huge number of particles forming this. It could be let's say condensate like liquid helium, but it could be let's say gas of Cooper pass in superconductor, and all this huge amount of particles is essentially described as a one particle quantum mechanical particle. So this is the Ginzburg-Landau concept, and if you calculate the current density for such an object, it is proportional, of course, to the particle density. It has also phase factor, which is modified by magnetic field in some manner that is probably familiar for those who have studied quantum mechanics. I will not explain everything, but let's say vector potential is a potential defining magnetic field. In principle, inside the superconductor, because of this Meissner-Ochsenfeld effect, if magnetic field is vanishing, also the current density is vanishing, right? This may be not obvious at first step, but it needs to be like this. So if this current density is 0, so we can rewrite this what is in the parentheses as an equation, right? So if we integrate both, so now we are considering the ring made of superconductors, right? So this ring is a repelling magnetic field, but magnetic field can still penetrate the inside of the ring, right? Because there is just vacuum or air, whatever. And so if we remove the magnetic field in the superconducting state, we expect such a ring would be, let's say, weak magnet, right? And this is because once we integrate this equation along the ring, we expect that this ambiguity of the wave function requires that phase, when we after making the loop around the ring, phase must be the integer multiplicity of 2 pi. also the integral over the integral of a vector potential is related to the stream of magnetic field flux, right, piercing the inside of the rings. This is what is called Stokes' theorem. So finally we get that flux piercing the ring is a multiplicity of some number. In Ginzburg-Landau is usually in Ginzburg-Landau derivations were usually m star and q star, which is some effective charge. It wasn't clear at this moment whether what is the charge of carrier in superconductor, but actually the flux quantum h over 2e was confirmed experimentally. It's also, if you do this consideration in the framework of BCS Bardeen-Cooper-Schiffer theory, it becomes that there needs to be factor 2 in the denominator. Okay, so flux quantization is confirmed experimentally. In some sense, this derivation is very similar to what is called Born-Sommerfeld quantization for atomic orbit, right? So such superconducting ring is a sort of artificial atom. So now the question is how to stimulate this atom such that it could show absorption and stimulated emission, right? So that's essentially what drives us to the Nobel Prize winners' works. Okay, so is the confirmation of this flux quantization important all the results. So now it's Josephson. Now this is Josephson as a 22 years old graduate student. He predicted his effect, and actually the Nobel Prize was awarded to him 11 years later, right? For what he has done as a student. On the blackboard behind Josephson, you can see the function, which is actually critical current of the Josephson function, which is also related to the magnetic field, right? That's quite important to understand the work of Nobel Prize winners, that this current could be tuned. Current could be tuned by a magnetic field. So more or less 1.5 years after Josephson made his prediction, Anderson and Rowell confirmed it experimentally. So as you can see, this little vertical part of the plot shows that at 0 voltage the current may flow through the Josephson junction. And in fact, what is funny about this plot is that curve B is actually in Earth's magnetic field, 0.44 Gauss. So to improve the property of Josephson junction, the Anderson and Rowell needed to reduce the magnetic field by let's say 2 orders of magnitude comparing to Earth magnetic field. So you can see how impractical this device should like, right? But to make it work, you need to turn off Earth's magnetic fields, right? This is very, very surprising from this point of view, that you can get something practical from this research. Okay, so now Josephson effect, just to maybe summarize key features. So essentially, you have a current proportional, superconducting supercurrent proportional to the sign of the phase difference between superconductors. The current in the direct current version, this current cannot exceed some critical current, and this critical current itself is related to the this is the limit of say low temperature and so-called narrow junction, right? So if the superconductors are very, very close to each other, the barrier of insulator is very, very tiny. So the supercurrent reaches the maximum, the critical current reaches the maximal value, which is proportional to the superconducting gap from BCS theory, to the normal state resistance, and some, let's say, there is elementary charge, and there is also factor p half, right? So this is also something, a consequence of BCS theory, which can be verified experimentally. Okay, so this is it. There is also an alternating current Josephson effect, much more important, in fact, that if you apply a constant voltage, right, across the junction, then the phase grows with time, with the speed given by 2e over h bar times the voltage, right? So in fact, the alternating current appears, and the frequency of this current is proportional to the voltage applied, and the coefficient is given by elementary constant. So it has Right, derivation maybe is something I would skip because time is probably running, but it's not difficult. It's not difficult. Application, let's say Josephson junction is now used as a quantum standard of volt, right? So if you have standard of Hertz from atomic clock, then you can use Josephson junction so to define the volt to second ratio with a very good precision. Then there is also a quantum Hall effect, which is used as a standard of Ohm. And what is missing in this story is quantum pump, right, which allowing to relate the ampere and the hertz, right? So let's say this quantum standards of volt and ohm can replace the old-fashioned, right, standard units used before. Okay, so that's the meaning of Josephson junction. First of all, is meteorology. Okay, but now also quantum computing. Okay, so to understand maybe this Nobel Prize paper a little bit, you need to take a look in what is called resistively and capacitively shunted Josephson junction. So like I said before, Josephson junction is also a capacitor and a resistor in one. So if you think about dynamics, first of all, classical dynamics of such systems, so you have some bias current, and you also may have some perturbation, right, due to let's say heat bath or due to microwave. So there's some constant bias current flowing through the system and some time dependent, say a little current. And if you calculate the total current flowing from such electric system, of course, the current flowing through the capacitor is capacitor times time derivative of the voltage across. The current flowing through the resistor is voltage divided by the resistance, and there is Josephson current. I wrote the bias current at this side of equation to have perturbation on the right hand side, right? So here you can rewrite everything because voltage is related to the time derivative of the phase via the second Josephson equation. Then you can write this equation simply as an equation for the phase difference between two sides of the junction. And if you take a look at this equation, you see that this is mathematically equivalent to the equation of motion for the pendulum. Right? So there is a pendulum, there is some constant torque, right? So there is some let's say rope here, so we have a constant torque, so the pendulum is not straight, it's just out of equilibrium. Of course, if this torque is bias current, right? If torque is too high, it starts to rotate, right? So that's what happens if we exceed the critical current in the junction. There is a highly tunable pendulum because we can tune the torque. We can also tune the length of the pendulum, which is related to the critical current, right? So these two factors can be tuned. And there is also some random noise, let's say, so some random impulses time dependent applied to this weight. So this is how it works. And essentially, if you write the, let's say, classical total energy, so kinetic energy could be expressed as a charge, right? Because charge is essentially a voltage times the capacity, right? So charge plays a role of the momentum here, and potential energy has this form, and this form of potential energy, which is what is called tilt washboard potential, right? So the slope of such a potential is related to the bias current, whereas the depth of this minima is related to the critical current, right? And you can tune all these parameters independently. I would say next step, which is not easy, is now due to a peculiar structure of the BCS ground state. this charge and phase can be considered as quantum mechanical variable, which does not commute, so there is an uncertainty principle for them, and then this Hamiltonian becomes equivalent to the Hamiltonian of anharmonic oscillators, right? So let's say Josephson junction trap in some metastable state, it could of course escape from the state, but there is also possible, if everything is precisely tuned, you can observe absorption and stimulated emission of radiation, which excite a transition between excited states of such system. All right. Okay. So now, okay, this is the reasoning why this phase and charge uncertainty problem comes from. Okay, what I want to say is simply that in physics is the most important thing is always most important question is always, do we need to guess some piece of knowledge, and can we derive, or can we derive it, right? So this uncertainty, this commutator could be derived. That's what I wanted to say in brief. So here are the, let's say, Nobel Prize papers. In first paper in 1984, they simply built a system and show that it works. So I will focus on these two papers of June and July 1985. So essentially, what they were measuring was the escape time, right? So suppose the system is properly tuned, Josephson junction is in its metastable state, the supercurrent is flowing, some radiation is applied, but not too strong. So we have a system in metastable state, and now the system can escape from this metastable state. If system escapes, then some voltage appears, right? So we can measure the time, how long the system lasts in this local energy minimum, right? And measuring average escape time, that was typically average over 100,000 of measurements. So it allows us to define the escape rate, which is inverse of escape time. And if the system is purely classical thermal, right, temperature is high enough, then it essentially escaped from its metastable state due to thermal, let's say, perturbation. So this escape rate can be very precisely determined by the system parameters. You see this frequency. This frequency is proportional to the critical current. Damping, of course, is proportional to the resistance, right? Everything can be calculated, right? So this thermal regime was understood. Right, actually, they found that cubic potential is enough to model the system. So these formulas corresponds to cubic potential. If you open the handbook, for example, Kittel-Knight, Ruderman on introduction to the mechanics, this anharmonic oscillator. Its oscillators with cubic potential are very familiar for physicists. This is why probably the reason they have chosen cubic potential just to describe the things. So now, also in this first Dunes paper, right, they have plotted what is called the escape rate in the presence of microwaves minus escape rate without microwaves, right? So if microwaves are applied, so the system is more likely to escape from the local minimum, right? Well, that's obvious thing. So they plotted for a fixed microwave frequency as a function of bias current, right? So they actually found there are some maxima corresponding precisely, because you can in principle you can change, right, frequency, but instead of changing frequency of microwaves, which is not easy, you can easier change this bias current, which also bias current is slope of this plot, but due to non-linearity, bias current also changed the resonance frequency, right? So they have observe the resonances corresponding precisely to the spacings between different energy levels, but it was essentially not enough, because such results also leaves the question open whether we have really quantum system, or we just have, let's say, microwave assisted thermal tunneling, right? That's if the system is in contact with the heat bath, it is not a surprise that some harmonic perturbation make escape easier, right? So what they did in the second paper is they actually defined what is called escape temperature, right? So let's ignore quantum effect for a while, and from escape time you can measure, let's say, effective temperature, right? What would be the temperature if the system is purely classical, and then plot this escape temperature as a function of true temperature. And what is shown on this plot is so-called quantum junction. Quantum junction is junction which has a relatively high critical current, and then by applying magnetic field, they have reduced the critical current. So open dots are for classical junction, and for this junction, this effective temperature is essentially equal to the real temperature, whereas for quantum junction, in sufficiently high temperature, we are able to cool down the system up to 19 millikelvins, right? So it's really low temperature as for electronic device that has all this power supplies and everything else. They found that this full dot saturates, right? So this escape temperature does not depend on the real temperature, but it can be explained by calculating this spacing between energy levels. So there is actually a macroscopic quantum tunneling, right? So that's what was shown by Clarke, Devoret and Martinis. And of course, we have quite a few concepts of quantum bits developed later. Here was some, let's say, 20 years old review by Yu and Noi. And this is how superconducting chips with Josephson junctions looks nowadays. All right, maybe a few words. I'm not sure which time I should finish my talk. Do I have like still 10 minutes or?
We have book time until 3:30. I think that it's up to you.
I understand. Yeah, so I think 10, maybe 12 minutes should be sufficient. Okay, so maybe a few words about Devoret, because as you see, Devoret was a postdoc during this Nobel Prize work were done with Clarke and Martinis. Devoret was a postdoc at Berkeley. Then he moved to Saclay, then to Yale University. Since 2023, he's working together with Martinis in Google Quantum AI, but he's also a professor in University of California, Santa Barbara. So let's say after this research on Josephson junctions, Devoret was working on quantum sensor, quantum dots. Actually, his most cited paper has nothing to do with quantum computers, apart from maybe very remote connections. It's work on carbon nanotubes done together with Rycerz Smiley, also Nobel Prize winner for Fullerens. Right, so that's it. Then he also was working on quantum noise theory of measurement. He contributed to the quantum algorithms for quantum error corrections. He have quite a few papers in Nature on this topic. And he was also involved in building the Willow chip, right? Employing advanced methods for quantum error corrections. Okay, here is the paper about Willow chip. Maybe I skip the details. So now Martinis. As you see, Martinis was a graduate student during this Nobel Prize paper were published. He did his PhD 2 years later with John Clarke, obviously. So you see that during the next, he needed to wait 38 years until his PhD thesis is properly honored, right? But he was not just waiting; he was also working on some other topics, including, of course, quantum sensors in 90s, when qubits decoherence in 2000, in early 2000, he was also involved in quite fundamental research on theory of quantum computing, quantum teleportation, maybe this violation of Bell states, very famous research. And since 2014, he's leading quantum AI lab, and he was involved in building what is called Sycamore chip, claiming quantum supremacy in 2019. Right, so that's Clarke. As you can see, this research actually the Nobel. The reason why Nobel Prize was awarded for some very old research on the Josephson junctions is probably the impact this research had on quantum computing business, because as you can see, this is the progress in quantum coherence. There's essentially two parameters characterizing quantum computer: the quantum coherence, the time of coherence, and the probability of errors. I'm sure there are much better expert than myself between the audience, so I would not go into very details. But as far as I understood, the bosonic qubits, including this involving this ion traps, are essentially better than qubits related on with qubit builds on Josephson junction, but there is no significant progress in this part of qubits, whereas for Josephson junctions we have a constant progress in coherence time observed during last decade, right? So probably in a short time the Josephson junctions overrule the bosonic qubits. Okay, so just to give you a short overview, so Nobel Prizes. So John Clarke started in 70s his research on squids, precise magnetometers, where all three Nobel Prize winners, Clarke, Devoret, and Martinis, meet together looking at Josephson junction in mid-80s. And then Devoret and Martinis goes to this superconducting chips involving Josephson junctions. Okay, so that's all essentially all from my side. So let me make a little acknowledgement. I thank Professor Józef Sparek, Professor Motyka, and Dr. Kuterba for stimulating discussions, hints when preparing of this talk, which is always not easy to prepare talk on the topic which is not close but not precisely related to my research, because people expect much, and these are actually many details in which I'm not an expert. I also thank very much Dr. Marian Bubak for invitation, and all the audience for your time and attention. Thank you very much.
Adam, many thanks for your talk, and especially not only just for explanation of for what they have got with Nobel Prize, but also for, let's say, some enlightening what they were doing after that. So it's and I think that it's interesting from the point of view of first of all, I think quantum computing, building a real quantum computers, I think that it is a good example of, let's say, how understanding phenomena, a kind of collective phenomena, yes. So this is because there is just from the point of view of quantum theory, there is probably just well, to some extent, applying the rule, use it and make a computation. Yes.
Well, I think the essence of the nice thing about this macroscopic quantum effect is that you can control the parameters Essentially with electric voltage. I wouldn't say I have kept some tiny details because in this original, for instance, in this original paper by Martinis, Devoret and Clarke, of course, this critical current were controlled with magnetic field, which is very inconvenient because you can't easily change the magnetic field from one place to the other. Of course, in these chips, it is controlled electrostatically, so there was also necessary to build what is called Josephson field effect transistor. But essentially, the difference between macroscopic quantum state and the real quantum state of atom is that you can't build electronic gate tiny enough to control the depth of potential in the atom, right? It's impossible. Whereas in this quantum effects, you can control everything using electric fields, microwave impulses, and this kind of thing. So I think it's the meaning of this work of Nobel Prize winners is that they had deep understand of physics, which are essentially new physics, right? Because like 20 years after this Josephson, not even 20, after maybe 20, okay, after this Josephson effects was demonstrated. So they have deep understanding of physics. They have built ingenious electronics because all the equipment were just built. You can't use a standard voltmeter or amperometer for experiment like this. So all the piece of equipment were built. So they did ingenious work on electronics, and it also has some practical implications. So all these three things met, and that's why Nobel Prize was awarded.
Yes, and it is all what is related to this superconductivity. It was a very nice slide with all these Nobel Prizes which were awarded for this research. Yes, so it's almost it looks like almost 100 years as a, let's say, something a little bit background for doing interesting research. And it seems that not just interesting research, but also of practical nature. I think that what because you mentioned about people who the last of these Nobel Prize winners who join Google, but I'm interested, curious what people from IBM who are also very heavily IBM, which heavily invest in quantum computing, how they are, let's say, using the results of this type of research. It may be interesting. I don't know if somebody in the audience knows something about it. But it's really from, let's say, observation in 1913 until this Nobel Prize. It's 100 almost 10 years, no, 12 years. So it's impressive phenomena, yes?
Right. As far as I understand, this Google AI is in fact joint initiative of Google and University of California, Santa Barbara. So I think both Devoret for sure has a position in Santa Barbara, and he's also working in Google. I'm not sure about Martinis, but this is kind of university and business cooperation. But right, history of superconductivity is very, very long, and we have probably every few years we may celebrate the anniversary of some discovery related to the superconductivity. Right. Right. The only problem is that it would be wonderful if high temperature superconductors could be applied for this quantum computing, right? Because then you could in principle operate in maybe maybe liquid nitrogen temperature, not in millikelvins, but it's probably a long way to go with this.
Well, I think that temperature is probably one of the keeping really the low temperature is something which make the cost of quantum computers very high. But I think that the main problem is something like decay of quantum states and all this noise. So I understand that this research also somehow contribute into reducing this quantum noise in application in quantum computing.
Right. It was essentially the first demonstration that you can observe between all this thermal and other noises. You can observe some feature of quantum states in macroscopic systems. So from this point of view, it was very. This is what is called quantum coherence. There are actually
coherence, yes.
There are actually some theoretical results suggesting that, because this is superconductor is also the example of system with spontaneous symmetry breaking. So if the system has spontaneous symmetry breaking, then there is some universal limit to quantum coherence, but this limit is very high. So this practical qubits on Josephson junctions still have some progress to make, but let's say quantum coherence time cannot be infinite, right? There always, even in superior quantum bits built on Josephson junction, there will be necessity to quantum error correction, right, due to some fundamental bonds. So that's really so in principle, if one would be able to build effective quantum computers operating on maybe 8 single atoms or particles, not on the macroscopic not on the macroscopic state, this coherent time could be longer. But let's say, as I saw this plot shows the opposite, right? This plot shows that this bosonic systems shows no progress, right? So the theory predicts some bound for this, but no bound for triangles, right? But the life shows something opposite, right? So that's also intriguing.
Well, let's give chance our colleagues in who are in the audience. I see that we have Jarek Miszczak, who is involved in quantum computing. So I don't know if somebody from the audience have a question or like to add to the discussion. No, so in this situation, I would like to thank you very much for this explanation. Now we are a bit clever about why the Nobel Prize was given to these three people from, let's say, for research, which were done quite long ago. Yes, so many thanks, and thank everybody for participation in this seminar. In a week from now, on Monday, we will have another Nobel Prize seminar. It will be about Nobel Prize in chemistry and in medicine. So, Adam, many thanks for being with us.
Thank you very much. Thank you one more time for the invitation.
Thank you. Greetings from Jarek Miszczak. Thank you for a nice talk.